Hello, welcome to our fourth lesson in our study of optimization 2. So in this video, we'll be talking about the Big M method, alright, which is a method under the simplex method for solving linear programming models. Okay, so I'm Guido Cranrandolph, a final year student of mathematics, KNUST, and I'll be taking you through this lesson. So don't forget to like the video if it helps you and subscribe to the channel if you haven't. Okay, so before you really understand this method, you have to make sure you have watched and understood the previous video on a simplex method. Okay, so the Big M method is used when we have to introduce artificial variables as the basis. So if you could recall, in our previous video when we were talking about the simplex method, right, when we were doing our iterations, because we considered the cases when we had less than or equal to in our constraint, changing that to the standard form, we're always adding slack variables, and those slack variables became the basis. Okay, because a basis is defined as a variable which appears just once in the constraint and has a plus one coefficient. And so with the cases with the less than or equal to constraint, that was satisfied. Okay, but when we have greater than or equal to constraint or the equality constraint, that doesn't hold. So we will have to introduce what we call artificial variables as the basis. So whenever we do that, then the method for solving that becomes a Big M method. Okay, so that's the reason why I said before you can really understand this method, you have to have watched the previous video on the simplex method and understand it very well. Okay, so if you haven't done so, please go and watch that video before this one. Okay, so it's assumed that you've watched the video on that one, so let's continue. So it says this happens when we have equality or greater than or equal to in our constraints. Okay, so when we have this or this in our constraint, that's when we mostly employ the use of the Big M method. So let's look at the contribution of the artificial variables to the objective function. So if you could recall, when we were talking about the slack variables, we said for the slack variables they have zero contribution to the objective function. Okay, when it comes to the artificial variables, that's not the case. So for the slack variables or the surplus variables, they have a zero coefficient contribution to the objective function. Okay, but in a case of the artificial variables, when a problem is a maximization problem, then their coefficient in objective function is minus m. Okay, minus m. But if it is a minimization problem, then their coefficient is m or plus m. Okay, so you should note the difference between the artificial variables and the surplus or what slack variables. Okay, for the surplus and slack variables, they have a zero coefficient contribution in the objective function, and that of the artificial variables have a plus m when we are talking about minimization, and a minus m when you're talking about a maximization problem. Okay, so note that the m that we consider in this case is a very very big number, very very big. Okay, okay, so that's the idea we are using here. So before one can use the Big M method, one has to always write the problem first in the standard form. Okay, so let's look at how we are going to take a problem and write it in the standard form. Okay, so let's consider this problem. It says minimize z equals 60x1 plus 50x2 subject to these constraints. Okay, so you can see that it's a minimization problem, and you can see that in our constraint we have greater than or equal to and greater than or equal to. Okay, So if you could recall, in our previous video, we said that when you are writing in standard form, when we have greater than or equal to, we write it in standard form by subtracting a surplus. Okay, so that means that writing the first constraint in standard form, we are going to have 2x1 plus x2, then we subtract a surplus minus s1. But because we want to use a big M method to solve it, we have to bring an artificial variable a1 equals 80. I'll tell you the reason why we do that. Okay, so let me send this one here. Then the second one is going to be x1 plus 2x2 minus s2 plus a2 equals 60. All right, so now we will have x1 s2 s1 s2 greater than or equal to 0, and then objective function now becomes minimize z equals 60x1 plus 50x2 plus 0s1 plus 0s2, because s1 and s2 are surplus variables, and the surplus variables and the slack variables, all of them, they have zero contribution to the objective function. Okay, but because it's a minimization problem, that's why the artificial variables will have a plus m, so plus ma1 then plus ma2. So this is the standard form for this problem that we have here. Okay, so the reason why we add the slack variables a1 and a2 is that you see that before we can use our big M method or the simplex method, we always need to get bases. Okay, and the bases were defined as variables which occurs just once in the equation, and they have a plus one coefficient. You see, when you talk about this s1 here, it has a minus one coefficient, so even though it appears once, it's not a basis. This s2 also has a minus one coefficient, so it's also not a basis. Okay, so that's the reason why we introduce the artificial variables a1 and a2. You know, they have a plus one coefficient, and they appear just once in the equation, so it helps them to be bases. Okay, that's why we introduce them. So with the first example, or this is the solution to it. So this is supposed to be plus. Okay, all right. So it's minimization problem. Minimize, right? Okay, so that's it for this question. I hope that's well understood. Okay, so here I even forgot to bring a1 a2. Okay, so this is a solution to that question. Okay, then this question says we are supposed to minimize this as well. So I hope now you can get it. Okay, so if the question says maximize, then as I said, the contribution of the artificial variables to the objective function is going to be minus m. Okay, but if it is minimization, then it is plus m. So I don't know why. Okay, so I think this problem was supposed to be maximized instead. Okay, so maximize. So we are maximizing 5x1 plus 7x2, then 4x1 plus 2x2. So subject to these constraints. Okay, all right. So we've done one for minimization. I want us to do one for maximization so that you see how it is done. Okay, so you see with this one, we'll first have to write the constraints. So we are going to get 4x1 plus 2x2. You see we have a greater than or equal to here. So that means we'll have to change it to equality by subtracting what? A surplus. So minus s1, then plus a1, because we need an artificial variable for that to be the basis, equals 20. Then the second constraint will be 3x1 plus 2x2, and you can see that one is less than or equal to. Okay, so that one we change it to equality by adding a slack variable, and that slack variable is going to be the basis, so there is no need to add an artificial variable. So this one will give us 16. And the second one, to have x1 s2, you could see that it is neither a less than or equal to or a greater than or equal to, so that means we can add or subtract. We can add a slack variable, we can also subtract what a surplus, but we still need a basis, so we have to add a slack variable to it. So now our objective function will be minimize, maximize 5x1 plus 7x2. So as I said, all the slack variables, they have zero contribution to the objective function. So 0s1 plus 0s2. Then because it is maximization, minus me1, then minus me3. Okay. Alright. So someone will ask, why do we have e1 and e3 and not e2? So I'm just trying to see the variables in the first constraint, the second constraint, the third constraint. That's why it is e3 and not e2. Okay, so yes. So in and this will be the non-negativity constraint. So in standard form, this is going to be the problem. Okay. So I hope now we understand and we know how to write the models in what their standard form. Okay. All right. So if you understand, then we are going to solve a problem. A very, very, let's say, um it's not difficult. It's not difficult. Just that it is plenty. Okay. So we are going to solve this problem here. So he says the copper field mining company owns two mines, both of which produce three grades of ore: high, medium, and low. The company has a contract to supply a smelting company with at least 12 tons of high grade ore, 8 tons of medium grade ore, and 24 tons of low grade ore. So note this keyword here, the at least. It says each mine produces a certain amount of each type of ore each hour it is in operation. Mine 1 produces 6 tons of high grade, 2 tons of medium grade, and 4 tons of low grade ore per hour. Mine 2 produces 2 tons of high grade, 2 tons of medium grade, and 12 tons of low grade ore per hour. It costs $200 per hour to mine each ton of ore from mine 1, and it costs $160 per hour to mine a ton of ore from mine 2. It goes on to say that the company wants to determine the number of hours it needs to operate each mine so that contractual obligations can be met at the lowest cost. Okay, we are supposed to formulate a linear programming model for this problem and solve using a simplex method. Okay, so what I'm going to do is that I'm going to let x1 represent the number of hours to operate mine 1, and x2 represent the number of hours to operate mine 2. Okay, mine 2. So we are going to get an important information from the question, which is going to help us construct our constraints. Then after that, we are going to get our objective function. Okay, so let's look at our constraint. The question. The question says the company has a contract to supply a smelting company with at least 12 tons of high grade ore, 8 tons of medium grade, and 24 tons of what the low grade ore. Okay, so this is a very important information that we need from the question. Then it goes on to say that mine 1 produces 6 tons of high grade, 2 tons of medium grade, and 4 tons of low grade. This is very important. And mine 2 produces 2 tons of high grade, 2 tons of medium grade, and 12 tons of low grade ore. Okay, this is very important. And it costs $200 per hour to mine each ton of ore from mine 1, and it costs $160 for mine 2. So this is also very important. It's going to help us formulate our objective function. Okay, so now with our constraint, So we let x1 represent the number of arrays to operate mine 1, and x2 represent the number of arrays to operate mine 2. Okay, so if you could recall from the question, it says when it comes to high grade ore, mine 1 produces 6, mine 2 produces 2, and the supply is at least 12, right? Then for the medium grade, this was it, mine 1 2, mine 2 2, and the at least 8. Then low grade ore was 4, 12, and 24. Okay, so constructing such a table really helps you to write your constraint in a simple way. So for instance, with this one, we are saying this is x1 and this is x2. So from here, we can construct the first constraint to be 6x1 plus 2x2, and at least the mathematical symbol for it is greater than or equal to. So greater than or equal to 12. And this will be 2x1 plus 2x2 greater than or equal to 8. And this will be 4x1 plus 12x2 greater than or equal to 24. So just by constructing this table, we've been able to construct or formulate our constraint from it. And the objective function, you see, it says that it costs $200 per hour to mine each ton of ore from mine 1 and 160. Okay, so taking those two, that means the objective function is going to be 200x1 plus 160x2. And as to whether we are minimizing or maximizing, you could see that in a question it said that the company wants to determine the number of hours it needs to operate each mine so that contractual obligations can be met at the lowest cost. So that means you are trying to minimize cost here. Okay, so the objective function will be minimize z equals 200x1 plus 160x2. So subject to these constraints, and we have the non-negativity constraint here. So we've been able to formulate our LP model now. And hey, if we were not able to formulate it, that means we couldn't solve the problem. Or if you should get anything wrong in your formulation, then that means the problem you are solving does not exist and you are going to get everything wrong. So the formulation of our model is a very, very crucial part of solving any LP model. Okay, so let's take note of that. And I think we learned that in our introductory video. Okay, so if you have problems with that, you should go and revise. So after writing it, or after getting our LP model, the next thing that we have to do is to write in standard form. And we have done that, right? That was the reason why I told you, like I taught you how to do that. So writing in standard form, oh, we are minimizing and I'm writing maximize. Why? So the objective function was to were to minimize the objective function, right? So let's see how you are going to write it in standard form. So this is going to be it in standard form. So we are going to minimize z equals 200x1 plus 160x2 plus 0x1 plus 0x2 plus 0x3. Then because it's minimization, the coefficients of the artificial variables are going to be m. So plus me1 plus me2 plus me3. Okay, right. And this is going to be the form of the constraint. Okay, so you can pause the video and write it out and try to see if you can figure it out why we got this. Okay, but we use the same concepts as the ones that we just did. Okay, so when it comes to the first constraint, our basis is going to be E1, here basis E2, and here basis E3. Okay, right. So now because we've been able to write it in standard form, we can initialize our simplex tableau. Okay, so there's a table for it. So we have the CB, which is the coefficient of the basis in the objective function. Then we have the basis. Then we have our x1 to e3. We have our right hand side. And we have our theta, which we are going to use to compute the minimum ratio test. Okay, so yeah, you should know how to fill this part of the table. So we just fill it from the coefficient of the objective function. So you can see with the first one, x1 is 6, x2 is 2, s1 is minus 1, then the rest are 0, e1 is 1, the rest are 0. So that's how we fill it. 6 2 minus 1 0 0 1 0 0. The right hand side is 12. Okay, so we use that to fill this parts of the table. Then after that, the CG is the coefficient of the various variables in the objective function. So you can see that when it comes here, that of x1 is 200, that of x2 160, s1 0, and so on. So that is what we write here. Okay, then this column is the coefficient of the basis in the objective function. So you can see e1 is what? M. There you can see e1, the coefficient is M, e2 M, e3 M. So that's why you can find your M there. Okay, all right. So after getting that, we have to compute our zj, and our zj is very simple to compute it. Okay, so our zj is computed from, so for instance, when we take this stage, it will be 6 times M plus 12, 2 times M plus 4 times M, which will be what? 12M. The one here will be 2 times M plus 2 times M plus 12 times M, which will be 16M. So we do that for all of them, right? And that gives us whatever we can find here. So when it comes to the right hand side, so it will be M times 12 plus M times 8 plus M times 24, which will give us 444M. So after that, we have to do Cj minus Zj. Okay, so when it comes to this is Cj and this is Zj. So let me increase this a bit. Okay, so when it comes here, the Cj minus Zj is going to give you 200 minus 12M, 160 minus 116M, M, 000, and the rest. Okay, and if you could recall, we said that for minimization problem, the stopping criteria is that all our Cj minus Zj should be greater than or equal to 0. Okay, so you can see that yes, this condition is satisfied, but these two are not, right? So most of the time, what we do is that we eliminate the more negative one, and you can see that since M is a very big number, 160 minus 16M is going to be the more negative number because of the 16M here. So 16M will be bigger than 12M, and you're subtracting it from 160. So you're going to get a more negative number than 200 minus 12M, alright? So that means that we are going to take that one to go into the solution, right? So that means that here our S2 is going to go into the solution, alright? So the more negative one will go into the solution, and based on that, we are going to construct what we call the minimum ratio test to know which of them will be leaving the solution. Okay, so S2. So that means to get our theta here, it will be the right hand side divided by x2 values. And so here it will be 12 divided by 2 because S2 here is 2. Here it will be 8 divided by 2, which will give us 4. And here it will be 24 divided by 12, which will give us 2. So we ask ourselves, out of the values we computed here, which of them is the smallest? You can see it is 2. So that means that that particular row is going to go away and we replace it with the column S2. So we call this the key column. And we call this the key row. And where they intercept, so you can see that they meet at what? 12. So 12 here becomes the pivot element. So that means that in our next iteration, we are going to focus everything around that. Okay, so S2 is going to enter the basis and A3 is going to leave. Okay, so when we take the whatever we have here, we can write it in this augmented matrix form. Okay, so you could see that 12 here is our pivot element. Most of the time what we do is that we try to make our pivot element has a coefficient of 1 because it's going to be the basis, and so it has to get a coefficient of 1. And we also try to make anything above it or beneath it 0. So when it comes here, the only way to make 12 1 is to multiply row 3 through by 1 over 12. So doing that is going to give us this, right? Then after doing that, we have our 1 here, fantastic. But we have 2 and 2 here, and we have to make sure they are zeros. So one of the ways that we can do that is to see row 1 is equal to row 1 minus twice row 3, and row 2 is equal to row 2 minus twice row 3. So doing that operation is going to give us this matrix here, and you have it in the form that we want. Okay, all right. And one thing with the big M method is that hope you can see that A3 is leaving the solution. Okay, so in our next simplex table, we wouldn't include the A3 portion. Okay, we will eliminate it. So our next table is going to be of this form. So we are going to get the CB basis x1 s2 up to A2, because we are going to eliminate A3 as I said. And the info that we get here will be based on the row operations that we did. Okay, so now our bases are A1, A2 and x2. You know the coefficient of x2 in the objective function is 160. That's why you can find 160 here. So with this one we do the same thing. Alright, so the only things for us to compute are the things in the red ink here. So we have to compute zg. So for instance, when you take this portion, it will be m times 16 over 3 plus m times 4 over 3 plus this, and that will give you this. So you get whatever you can see there. And when you subtract cj minus zj, you get 440 over 3 minus 20 over 3 m 0 and the rest. Okay, so you can see that out of all what we have, the rest are positive with the exception of this here and that here. But this one is more negative because minus 20 over 3m here will give you more negative value than the 1 over 3m. So that means x1 is going to enter into the next iteration. So we have to look at the column which has to the row which has to leave. Okay, so this one is the key column. So we have to look for the key row. So to look for the key row, we have to use the minimum ratio test. Okay, so to compute the one here, it will be the right hand side divided by the values for x1. So it will be the one here, for instance, will be 8 over 16 over 3, and that's giving us 3 over 2. Then this one will give you 4 over 4 over 3, which is giving you 3, and this will be 2 over 1 over 3, which is giving you 6. So you can see that the least value here is 3 over 2, which is 1.5. So that means that the row A1 is going towards leave for x2 to enter the basis. Okay, so yeah, that's it. So that means that in our next table, we wouldn't include A2 since it is leaving. Okay, we wouldn't include A1 since it is leaving. So we can now write our augmented matrix for the entries here. We always write this for the entries here. So that because here the pivot element is 16 over 3. Alright, that's where the key column and the key row meet. So we have to make sure that we make the coefficient, we make it 1, and everything under it should be 0. Okay, so we can do that by saying row 1 is equal to 3 over 16 row 1, and doing that will give us this. You can see now we've made it 1. Okay, then we have to make this 0 and this 0. So the only way we can do that is to say that row 2 is equal to row 2 minus 4 over 3 row 1, and that row 3 is equal to row 3 minus 1 over 3 row 1. So doing that is going to give us this here, and it is of the form that we wanted. Okay, so we can do our next iteration. So yes, doing our next iteration, we are going to get this nice table here. I hope you understand. So now the coefficient of x1 in the objective function is 200. So you can see 200 here. That of A2 is m, that of S2 is 160. Then the ones that we are going to compute are the things in what red. Okay, and you know how to do them by now. Okay, so doing them will give us what we can see here. Then cj minus zj will give us 0 0. We have 27.5 minus 1 over 4m and the rest here. So you can see that this is more negative. Okay, because minus 1 over 4m is more negative than minus 1 over 8m. So that means s1 is going to enter into the solution, but which of them the basis is going to leave? So we have to do the minimum ratio test to know that. Okay, so the only way to do that is to multiply the right hand side by the s1 values. So this will be 3 over 2 divided by minus 3 over 16. That will give us minus 8. And one condition is that the theta should always be greater than or equal to 0. So that means that since it's negative, you are not interested in it. When you do 2 over 1 over 4, you get 8. When you do 3 over 2 over 1 over 16, you get 24. So In terms of the positive values, the 8 is the least, and so that means A2 is going to leave the basis for S1 to enter. Okay, so the pivot element is going to 1 over 4 because that's where they meet. Okay, all right, I hope we get it. Yeah, so we write our R in this form, and we have to make this 1 over 4 1. So the only way to do that is to multiply row 2 throughout by 4. So doing that gives us this. Then after getting that, we have to make this 0 and this 0, and we can use this relation here to do that. All right, so when you do that, you are going to end up with this here. We've done a great job, right? Yes, that's cool. So after doing that, then we represent it in our table. So you know now A1 is going to leave because we are done with that. You're not interested in that. Okay, so the coefficient of S1 is 0. S1 is like the surplus variable. S1 is 0. S2 is 160. Then we have this nice table here. So we only compute the things in red. You see, if you really understand what you are doing the iteration is very simple, right? Is there the decision that you have to know which kind of decision you're supposed to make? So when you compute the things in ZG, then you're going to get this wonderful table here. So you can see that everything that we have here is positive with the exception of the -5 here, right? So that means that still the stopping criteria is not met. Okay, so since S3 is the more negative value here, it will have to enter into the solution to take away one of the bases that we have. Okay, so to do that we have to use a minimum ratio test. Okay, so um the one here will be 3 over 1 over 8, which is 24, 8 over 1 over 2, which is 16, and you know we have a negative value here, so we don't consider that. So out of the positive values, 16 is the smallest, is smaller, right? You're comparing two things, so it's smaller. Okay, so that means that S1 will have to leave the basis for S3 to enter. So in our next iteration, we write this echelon form. So we now what is the key? So this is the key column, the key row. So what's the pivot element? The pivot element is half, right? Okay. So that means that we have to make sure this one is 1. So the way to do that is to multiply row 2 through by 2. When we do that, we get this. We have to make sure this is 0 and this is also 0. So this is a relation we can use to do it. And when we do that, we are going to end up with this matrix. Okay. Alright, so after doing that, we can construct our table, compute our ZGs, and now when we get here, are going to get 200 minus 200, 0, 160 minus 160, 0, 0 minus 10, 10. You can see that all our CJs minus ZJ are positive. So that means that hey, we are supposed to stop because the stopping criteria is met. So we are going to terminate our iteration process. Wow, it's been a very long journey, but finally we have an optimal solution. Yay! All right, so um, now we have our optimal solution because the stopping criteria is met. So we have to read the values for S1 and the rest and Z from the table. So the value for S1 is going to be the right hand side, so it's going to correspond to 1. S2 is going to be 3, and this S3 will be 16, and this Z will be the minimum cost. Okay, so since CJ minus ZJ are all positive, hence the optimal solution is arrived with the value of variables as S1 is 1, S2 is 3. We can include this as 16, and our minimum. So our minimum cost now will be $680. So that means that if we operate mine 1 with 1 hour and mine 2 with 3 hours, that's going to give us a minimum cost, and that's going to be a cost of $680. Okay, so thank you very much for following. I know this has been a long journey, but finally we have landed. We thank God for that. So all the best and see you in the next lesson.